In stats, we wrapped up chapter 3 by looking at 2 different examples. So it's all the way in the back of your handout. And in this one, they're using foot length to predict height. You can see that in the scatter plot there, with foot as the x and height as the y. And then on the right graph, you see we have a residual plot. Many times they don't give you the data set and they just give you this weird computer printout. The row that says constant is the y-intercept info. And the row that says the x context, it's not always foot, x context is the slope information. So that means for the coefficient, this is the actual y-intercept. And this is the slope. These two right here, these are called standard errors. We'll deal with it more in the spring. So that first one is the standard error of the y-intercept. It's like how it varies from the actual value based on the sample. And this is standard error of the slope. These numbers over here, we'll deal with those in the spring. We don't need to mess with those. So that's spring semester. We'll wait on that until, I think, March when we'll deal with that. The S right here, this is the standard deviation of the residuals. Let's write a better E there. And obviously, this one is r squared. So we have one on here that is left that I haven't talked about. And it comes into play when you have very unique experiments. And they have never, ever approached it or used it in AP Stats. You'll definitely use it if you go into data analysis later on in life. But for the sake of the AP test, we will never use r squared adjusted. Notice r is not here, but yet we have r squared, so we can just square root r squared and get r. Make sure you note the sign of the slope, though, because the sign of slope should be the same as the sign of r. So in this problem, they ask us to write the least square regression equation and define our variables. So based on this table up here, if you need to hit pause or take a picture of it and then work the problem, go for it. But the way that you should write it is height hat, because this is the predicted height, equals y-intercept, I'm losing my mind, plus the slope. Slope-intercept. What is a slope-intercept? And that is all they are asking for on part A. When they say define the variables, we have 2 variables, foot length and height. And so by writing them in that spot, we are defining the variables. I guess your other option is you could use y and x there, and then off on the side you could say x is foot length and y is height. But I don't know, this way I feel like it's more efficient. On part B, we need to interpret the slope, which is 2.7469. And I throw it over a 1, and you need to talk about the change in y, height, over change in x, foot length. So I typically write that on my paper, and then I put it into words. On average, or you can say it is predicted, or typically, or there is an increase of about 2.74, as long as you have some kind of word in there saying it's not like a fact, that it's typically this value, then you're going to be fine. There is an increase of 2.7469 centimeters in height for each centimeter of foot length. For every 1 centimeter increase of foot length. That's another way to write it. All right. Correlation, in the table, it told us that r squared is 48.6. So let's convert it to a decimal. And then to get r, we can square root that. And we get 6971. There is a positive. Oh, I forgot to double check. Remember, your slope sign and your r sign should agree. Slope is positive, so is r. So there is a positive, moderate, linear correlation of 6971 between height and foot length. Last question, is a line an appropriate model? So a question that they're asking, like another way they could ask this question is, what condition must be true to use a linear model? Like, that's another way they could phrase this. It's the same question. Is a linear model appropriate? I see that this is a different question. Is the linear relationship good? That's a different question. That's when you look at like the scatter plot and you look at R and talk about how strong they are. So that's a different question. D is asking what must be true, and notice we have a very random looking residual plot. I'll scroll to it in case you didn't look at it. So the graph on the right, I do not see a pattern, so we want to say yes. It is appropriate to use a linear model for height and foot length because there is not a pattern in the residual plot. Kind of crowded at the bottom of the page. All right, let's reread it. Yes, it is appropriate to use a linear model for height and foot length because there is not a pattern in the residual plot. So what I'm trying to say on part E down here that I randomly wrote, that would be a completely different scenario, different question. If they were asking like how strong this relationship is, then you talk about the scatter plot, then you talk about R. You can compare different models on a question like that, but that's not what it's asking. It's just asking you to look at the residual plot. That's what's implied anyways. All right, so try another one. I would recommend that you hit pause and you give this one a try, this last problem. Maybe hit pause and read. Look at the scatter plot on the right, residual plot on the left. Look at the data printout. And then answer these 6 questions. I can't quite get it all in one screen. There we go. All right, here we go. We know that test score, predicted test score hat equals 85, 706 minus 1.1171 times rho. And that is all they want for part A. The slope is negative 1.1171. So I would say on average there is a decrease of 1.1171 in test score for each row, for each additional row, for let's say for every one row. I don't know, you can play with the wording there. I think that'll work. Correlation, be very careful. First of all, R squared is 0.047, so be careful with that. And when we square root it, it's negative. Notice the slope is negative, so is R. So we should get negative 0.2168. There is a negative, weak, linear correlation of 2168 between test score and row number. S is something brand new. In this problem, it is 10.0673. And that standard deviation is calculated by taking each of the residuals in this graph on the left, and it, in a way, averages them. So there's more involved in that. You saw a formula yesterday. It's sum of the squared residuals divided by n minus 2, and then you square root all that. So when you do that, it's kind of like saying the average distance from this least squares equation line is 10.0673. So on average, my stylus is struggling to write on this screen. On average, the predicted score is 10.0673 away from or within the actual score. Because that's what a residual is, right? The difference between the two. We've never done r squared. We talked about it. Well, I guess we did it one time, but here we get 0.47. You could leave it like that. I typically just use a percent, so I would say something like 4.7% of the variation in y, so of the variation in test score, because that's y, is explained by a linear relationship with x, in this case, with row number. Is a linear model appropriate? And if you look at this residual plot, yes. The residual plot does not have a pattern. A linear model between test score, I'm really struggling to write it with the stylus, and row number is appropriate. All right. Hope that makes sense. See y'all later.